todos. Me tocó a mí presentar a Enrique, a quien no lo conozca. Es Enrique. Él obtuvo su licenciatura en la Facultad de Ciencias de la UNAM y su doctorado en la Universidad de Texas en Austin. Inicialmente, él trabajó en cuestiones de dinámica de sistemas no lineales, turbulencia, cosas de ese estilo, y eventualmente redescubrió la gravedad, que es la base para el modelo de GHC que en el grupo de exturbulentos hemos estado empujando. Es un modelo, para los que no sepan, es un modelo de formación y evolución de nubes moleculares que consideramos el correcto. Bueno, regresando a Enrique, él tiene 117 artículos publicados, arbitrados, que son casi 10.000 citas. Fue director del IRyA, obtuvo el premio de la Sociedad Mexicana de Física en el 2019, el premio Universidad Nacional en Ciencias Exactas en el 21, entre otros. Recientemente publicó un libro titulado Interstellar Flow and Star Formation. Quisiera hacer notar que es flow en singular. Eso es un punto bastante interesante del libro. ¿Qué más hay que decir? Tiene un programa de radio. Es jazz fusión, pero bueno, nadie es perfecto. Y pues, ¿qué más? ¿Ya?
Gracias. Típica introducción de Gilmo. Gracias por la introducción. And I think I'm going to be speaking in English. That's trying to keep the spirit of international audience, especially since we have plenty of English speakers here in the audience today. And so, yeah, my talk today is going to be dealing with our rediscovery of gravitational collapse. And you'll see what we mean by that as we go along. But basically, we tend to think of gravitational collapse as a sort of isolated event. At least that's how many astronomers think about it. We think that stars just sort of pop out, you know, like little flowers from the ground, but that's not really what gravitational collapse is, or what the gravitational force does. And so that's what I would like to be talking about. And it's not moving. And I would like to take the opportunity to make a commercial that this talk is mostly based on the contents of one of the chapters of the book that Gilberto just mentioned, which is called Interstellar Flow and Star Formation. And the idea of flow being in singular is that we want to think of the interstellar medium as a fluid. And we want to think of it as how it flows from one place to another, in particular as a consequence of gravity, but also as a consequence of all the other forces that are acting on it. But it's a flow, it's a fluid. And we used to think, when I was young, when I was in graduate school, we used to think of the ISM as in terms of what my supervisor used to call the meatball soup. So we used to think of like a broth and with little meatballs in it, you know, so it's like just, and there are papers that even treat these little blobs that are the clouds, they treated them almost like bowling balls. Because they were talking about the Venturi effect around the clouds as they were flowing through the medium. Really weird. And so my supervisor used to think about it. We used to call that as the meatball soup model of the ISM. And instead we want to think in terms of fluid that's just moving around, going from place to place. And I'm going to be pointing on the screen for the people on Zoom. And it contains a discussion of turbulence, both compressible and incompressible, contains thermodynamics, and in particular in relation to the phase transition from the atomic gas from the diffuse gas to the dense gas that then leads to the formation of molecular clouds. It deals with the virial theorem, in particular in cases out of equilibrium, because it is very common. I've encountered cases where people confuse the virial theorem with virial equilibrium. And of course, the virial theorem is an equation, the virial equilibrium is a condition. And so it is very important in terms of flowing fluids to think about systems that are out of equilibrium, particularly in the presence of turbulence. It contains a part of self-gravity, in particular collapse, which I'm going to be discussing about, and then it tries to apply all of this to the evolution, to the formation and evolution of molecular clouds and their and the evolution of their star formation activity. So with that, this is a list of. Pardon?
Is the book already in the library, or do we have electronic access to it?
It's an ebook. So in fact, there was the QR codes where you can download it from. But we are asking for. No, unfortunately, it's free for people subscribe to the AASIOP series.
And you know it's already in the library?
I've requested it. That's
It will be.
literally.
There should be, but if somebody wants a copy, I have.
Okay, so this is the list of the collaborators I've been working mostly with for the work I'm going to be showing today. And the outline is, first I would like to emphasize the idea of collapse as a flow. Then I'll go and revisit the old notion of spherical collapse, as for example dealt by Frank Hsu, because we are very much used to the idea that the gravitational collapse in molecular cloud cores happened from the inside out. But it turns out that it's in most, I would say in almost every case, it's the other way around, it's outside in. Then how does the density profile, the radial profile evolve over time, and how that relates to the accretion rate? And then how, when you do have turbulent density fluctuations in the cloud, how the more massive density fluctuations collapse first, and then the least massive ones collapse later. Then I would like to talk a little bit about the fact that once a core is collapsing, its mass grows together with the stellar mass it contains. And this has several implications for the correlation between the mass of the most massive star and the mass of the cores they live in. And then finally, I would like to talk about anisotropic collapse and the evolution of the energy budget of clouds, but I don't think I'll have time for that. So the misleading term collapse. And I went out and looked at the dictionary for the definition of collapse, and as a verb, it is expressed like that. It is to fall or shrink together abruptly and completely, to fall into jumbled or flattened mass through the force of external pressure. And as a noun, it is a breakdown in vital energy, strength, or stamina. But in general, it sort of implies a sudden sort of deflation. No? And in astronomy, we also use it very often like that. We think of gravitational collapse as a sudden and isolated event. And like I said, for example, all these ideas that there's a threshold density or threshold column density for the onset of star formation sort of has never clicked on my mind, because somehow you need to go from the lowest densities to the highest densities to form a star. So you have to go through the entire density range. And so what does it mean to have a threshold density for star formation to happen? And there's a very interesting paper, for example, by Lee Hartman and Andy Burkert, saying there's no thresholds, it's just timescales. As you're closer to or at higher densities, then the timescales are shorter and you begin to associate star formation with the background density. But it's not a matter of really there being a threshold below which there's no star formation and above which there is. Yet analytical and numerical solutions describe a flow and which spans a very wide range of scales. So let me start at the beginning. So with the notions of spherical collapse. And this has been investigated analytically, most often through similarity analyses. And these analyses mean that you define what's called a similarity variable, which is essentially the radial variable divided by the time variable. So that means that the time is usually considered to span the entire range from -infinity to +infinity. And so minus infinity to 0 corresponds to a contraction stage of the cloud where you have not formed the singularity yet. So in our terms, you have not formed the star yet. So just the gas is accumulating. And then from t equals 0 onwards, then you do have a central star, and then you have the singularity has already formed. So this time, and then the radial variable is rescaled according to the time with this similarity variable, right? So you could think of this as a sort of co-moving coordinate for the description of the gravitational collapse. So, and it has been done in isothermal conditions and spherical geometry. So to me, although Schu's paper is probably the most cited paper, Schu's from 1977, is the most cited paper about gravitational collapse, spherical gravitational collapse. To me, sort of the Bible for gravitational collapse is the paper by Whitworth and Somers from 1985, in which they essentially try to cover the entire spectrum of possibilities for the gravitational collapse. And so they identified the asymptotic solutions for the collapse. And these asymptotic solutions, so very close and very far from the central point where the singularity arises. And these asymptotic solutions have two spatial regions and two temporal stages. So the spatial regions are, of course, an inner region and an outer region, and that corresponds in this similarity variable to the similarity variable psi less than unity, and the outer region is larger than unity. And the early stage corresponds to the prestellar phase of collapse, for which the time is negative, and the late stage corresponds to the protostellar stage of collapse, for which the time is positive. And these two temporal stages are separated by the moment of the formation of a singularity, the moment of the formation of a star in our terms. Each one of these regimes is characterized by different density and velocity profiles, and that's what's very important for our purposes. So during the prestellar stage, for negative times, since there's no star in the center, only the gravity of the gas is important. And it is then consists of the inner region, and in this inner region, which we said corresponds to psi less than unity, so the white area here, and it has a flat density profile. Here is shown here. Of course, this involves the thermal pressure, so the thermal pressure is dominant here. The gravity of the material inside any coordinate, any value of the variable here is negligible, and so essentially this entire region is dominated by just pressure balance. But and then the inflow speed, which is negative because it's inwards, is linearly scaling with the radial position. So the velocity scales linearly with radius, meaning the velocity is 0 at the center. So this is very interesting. At the center, the material is not moving. And you have a velocity gradient so that the velocity is increasing outwards. That's the asymptotic solution for the equations of the collapse in the inner region. And in the outer region, then now here, the central gravity of the gas now is dominant. And so now you have a decreasing density because you need lower and lower pressures from the outside to maintain equilibrium or to balance the complete force balance. But the gravity here is not negligible and becomes increasingly important as you go out. And that corresponds to this rho goes like psi to the -2. And psi, I'm going to be saying the radius in most cases. So here the density goes like r to the -2, and the inflow speed goes to a constant minus an inverse term in the radius. So, and this constant is, if it is present, then the velocity just goes uniformly outwards. But this is a little bit strange because this means that the entire universe is falling onto you. right? Because it keeps the same speed at arbitrarily large distances. So often, and we will get to this in a moment, you can take this first term to be zero. You impose the condition that the infall speed is zero at infinity, and then the next order term is this one here. I keep losing my pointer, which goes inversely with the radius. Okay. Then during the protostellar stage, which here is signaled with the dotted points and corresponds to a positive time scale. To a positive time variable, the inner region now is dominated by the gravity of the central star. So in this inner region, now the self-gravity of the gas is still negligible, but the gravity of the central star is important. And that gives rise to this density goes like r to the minus 3/2 scaling, and velocity goes like r to the minus 1/2 scaling. And this is the famous Shu solution for the inner part. On the other, pardon?
May I ask a question?
Sure.
So in the outer region, in the case where V infinity is zero, and your velocity is proportional to whatever r, should the density also be whatever r?
Perhaps the density should go down again. Yeah, that I have not checked. But yeah, otherwise you do not keep the same. You don't keep the same mass flows. Yeah, you're right.
Enrique, quick question about the definition of psi. The way it is defined on your previous slide seems like it's a causality statement. Anything less than one is because it seems to be in causal contact, and the envelopes are not in causal contact because there's a speed which is Cs that you define, the sound speed. Is that the way to think about the separation of the two regimes?
Yes and no. That's the way it used to be thought about in the case of the Shu solution. And you have, in that case, you have a boundary at which you reach zero speed, and then you have your core in equilibrium.
Yeah.
But, and that boundary expands at the sound speed, right?
Yeah.
That's the classical solution. So in that sense, yes, it is. So there is a connecting, an information boundary there.
Yes.
But the thing that I'm going to get to in a second is that when you do consider prestellar stages of collapse, then the flow is already infalling from larger distances. And so the boundary is not between a hydrostatic region and an infalling region, it's between two different regimes of infall. So yeah. And so during the protostellar stage, precisely, you have that. And so the inner region is, like I said, is dominated by the gravity of the central star. And you have the same scaling. Rho goes like r to the minus 3/2, and V goes like r to the minus 1/2. And the outer region keeps the same shape as the prestellar stage, because we're assuming that that's coming from way back in the past. So several notes about this. The inner region of the prestellar stage is not self-gravitating, and that's what I was mentioning. That's why you have a flat density profile on the top. But the density is increasing in the central part over time. How does that happen? It's being compressed by the infall of the external material. So it's essentially, that means, this explains directly why some people have observed what they call pressure-confined clumps or cores. For example, this paper by Charlie Dada and collaborators in 2008, they reported that a number of dense cores in molecular clouds apparently are locally gene-stable, so they are not self-gravitating. And so they concluded that they must have been pressure-confined. Well, in a sense they are, but they are not thermal pressure confined, they're Ram pressure confined, they're being compressed. In this solution, you still have the central part, and the central part is still G-stable, but it's being pushed or compressed by the collapse of the outer parts. And so you keep your central density flat, and then you have the infall of all of the other material. So these cores that have been reported to be pressure confined may just as well be cores that are the central parts of the prestellar stage of collapse. And so in that case, what you are actually doing is, oh, I forgot to say that in these cases, for when people say that they're pressure confined, you often hear people saying they are confined by the weight of the external cloud. But that is impossible. Why is that impossible? Because an equilibrium solution that for those of us who have studied the equilibrium solutions of the thermal isothermal sphere, there's this what was I going to say? There's this central part. There's a maximum ratio between the central density and the outer density, beyond which the solution is unstable. So these are called stable. So it's the marginally stable Bono-Everett sphere. These spheres that are confined by pressure are called Bono-Everett spheres, and there's a limiting Bono-Everett sphere beyond which, if the central density is the ratio of the central density is higher to the outer density is larger than a certain critical value, which is about 14, then the sphere is unstable. So if you have your central core confined by the weight of the entire cloud, essentially what you have is an unstable Bono-Everett sphere. And so it cannot be in equilibrium, it's unstable. So that's not possible because precisely of that. So what is actually happening is that the central part of the sphere is like a Bono-Everett sphere, but it's subject to a continuously increasing external pressure because the outer parts are coming onto it. And so the central density is just increasing, but the outer part, and it's increasing not because of its self-gravity. This central part is not self-gravitating, but it's just being compressed by the inflow of the external regions, okay? So, and that is why precisely, in fact, in that paper, it was shown that the apparently pressure-confined cores lie along the same line in a plot. I don't remember exactly what they were plotting, but they are an exact continuation of the unstable Bono-Everett spheres. So they had the central cores that were supposed to be genes stable, and the outer cores that are genes unstable, and they line up in precisely a perfect sequence. And this can be understood because they all form part of this collapse with a genes stable central part. Okay. So the second part is that the second note is that the prestellar collapse occurs from the outside inside this in this inner region. And it can be shown here. I don't have time to show it, but that this variable is also equivalent to the radius divided by the gene's length corresponding to the central density. And that means that this is essentially this is on the order of the genes at a distance of the order of the gene's length from the center. So what you have is that this is what's been said here, and this has been found by Whitworth and Summers themselves, and Quito also has pointed it out. And so what this means is that the prestellar collapse also, because the prestellar collapse corresponds to the negative time, if you look at where the position of this non-dimensional variable equals to unity is in physical space, if the time is coming from minus infinity to 0, so its magnitude is decreasing. And so to keep this value equals to unity, the radius must be decreasing. So during the prestellar stage, this boundary in physical coordinates and in the radial coordinate is falling into the center. So the central part is shrinking, and eventually what you get is that this boundary reaches the center in a finite time. At that moment in time, you have this large velocity. So this large velocity, which lies on the outside, is approaching the center and hits the center, and that constitutes an outside-in collapse. And when this peak reaches the center, then you develop an infinite gradient of the velocity, and that at that moment you form the singularity. So and you form a shock at the center. So that marks the transition between the prestellar stage and the protostellar stage, And also from that moment on, this shock propagates outwards, and that marks the boundary. Now, for positive times, now this boundary moves outwards. And so this shock that formed at the moment of singularity formation now propagates outwards. And now that is the boundary, the division between the inner and the outer regimes.
Very similar to supernova.
To what?
To core collapse supernova.
I guess so, yeah.
I mean, obviously the physical regime is totally different.
Yes.
But the sort of the scenario of events seems to be very similar.
Yeah, I guess the physics is the same. No? But the interesting thing is that we sort of forget that there's a full prestellar stage and that all of this stuff is happening. No? Okay, so that means that during this stage, the collapse is propagating inward. So it's a sort of tsunami falling onto you, know? So the large velocities are coming at a distance and they're approaching you and eventually they hit you. So precisely the question is, where does Schu's famous solution, inside-out solution, fit in? And this is very interesting. It's a perfectly valid mathematical solution, but it's a very special solution, which was assumed to start from a singular isothermal sphere. And he made this choice because of very valid reasons as well. He chose the singular isothermal sphere, which is essentially an r⁻² density profile all the way from the center to infinity. And that has one G's mass at every radius, okay? But it has a singularity at the center. So essentially, the reason to choose this profile is because this is the only self-similar solution for in hydrostatic conditions. So it is the only self-similar hydrostatic solution. So it's like the limit of the Bonner-Everett spheres when you form a singularity at the center. He also assumed, a zero impulse speed at infinity. So essentially, that is you starting from an equilibrium singular isothermal sphere. And then he assumed to perturb the center a little bit so that now the center begins to collapse and now you have a wave propagating outwards, a collapse wave propagating outwards. And in that case, the solution is like this. You have the rho goes like r⁻³ at the center and velocity goes like r⁻⁻². But this solution terminates here at this radius of unity in the similarity variable, and outside of that you have zero velocity and an r⁻² density profile, which was the hydrostatic solution. Unfortunately, the singular isothermal sphere is impossible to happen in nature. Why? Because essentially you're assuming that you have a singularity that developed under hydrostatic conditions. More mathematically, the singular isothermal sphere is the most extreme case of the Bonner-Everett sphere. So where the central flat density part has shrunk to zero size. And so essentially you have a singularity at the center. And so somehow Schu's solution bypassed the entire prestellar stage of the collapse. So Schu's solution starts at the moment of the start of the protostellar stage, the later stage. But in practice, that cannot happen. So because the hydrostatic solutions are regular, so they are not singular, they have finite densities at the center. What you have is that, and because there's a limit for that configuration above which you are unstable, it means that any configuration that starts from equilibrium must have become dynamic way before you develop the singularity. So what does that mean? Well, it means that you must consider that you have had a stage of prestellar evolution during which you have velocity, impulse speed that extends way beyond this psi=1 boundary. And well, this is a number of some solutions, numerical solutions that I did for the equations, just showing that this A constant is the measure of how much you deviate from the singular isothermal sphere. And so when you're very close to the singular isothermal sphere, indeed you have the shoe solution inside and then a vanishing velocity field. This is the velocity outside. But as soon as you start to deviate, your initial condition starts to deviate from the hydrostatic condition, then you see that your velocity profile essentially is, your velocity profile almost has no discontinuity. And what changes is the slope, but you don't have a vanishing speed at large distances. So this is quite important. This was already reported observationally by Lee and Myers and Tafaya in 2001. They were saying, we have observations that in which the cores seem to be collapsing much further out than the limit that required by the shoe solution. So basically, they were already reporting something consistent with this configuration here, rather than this other one with a vanishing velocity outside the sonic boundary, so to speak.
It still drops by several orders of magnitude.
Pardon?
The speed still drops by several orders of magnitude.
Well, yeah, on the outside, the speed, this is the second this is the second term in the asymptotic solution. So it goes like 1/r. So this means also that this raises a question as to whether our typical understanding of how a signature infold line profile arises, and why is that? It has been said, for example, from papers in the 70s and 80s, and this is from a review by Neil Evans in '99, of what is the spatial configuration that gives rise to a molecular line profile, which is what's considered the signature of gravitational collapse. So these infold profiles, as they are known, as they are called, pardon me? What happened? Okay. So that's a problem of looking at my screen here, right? So we have collapse line profiles, which are characterized by having a self-absorption dip and two peaks which are asymmetric, so that the blue shifted peak is higher. And this is, I don't have time to go into the entire description of how these profiles arise, but they are thought to come from precisely the shoe configuration for the inside-out profile. So you have an increasing velocity inwards and then an outer hydrostatic envelope. But if we consider that real cores should have an extending outside velocity, and in the inner parts, they actually may have the reverse velocity profile, then we should revise, and this is a project that we have had in, dormant for several years, but we should revise what is the morphology or what is the tomography of a dense core that gives rise to this type of profile, because the underlying assumed density and velocity profiles are probably not appropriate. Okay, that's that for the spherical collapse. Let's see. So I'm only going to make it to 1/3 of my talk, I think. But anyway, so now I would like to shift from the self-similar solutions to the non-self-similar solution. And why is that? Why is that? Well, of course, we know that self-similar solutions apply to regions that are far from either the initial conditions or the boundary conditions. But really, real cores are not very far from their boundaries. And especially, we must assume that cores begin to collapse at some moment in time. They haven't been collapsing for the entire age of the universe. They form, and then they suddenly, at some point, become locally gene unstable and begin to collapse. And so, how do they grow? How do they evolve? And this is what we want to discuss now. What is the transient evolution of the prestellar stage of collapse? And this was done in a paper with Gilberto Gomez and Aina Palau in 2021. And here we again looked at isothermal spherically symmetric situations, but now we started assuming an almost uniform density initial condition. So something like this. No? So this is radius and this is density, and we just assumed an essentially flat initial condition, but then we considered the gas inside a 1 Jeans length of this corresponding to this density. We consider the boundary of what will become the core to be 1 Jeans length of the background density. And then we cheat and we assume that the density keeps a power law shape at all times. Real numerical solutions show exactly what I was talking about before. This is from Larson's famous 1969 paper, in which you have the initial density, but then as time goes on, your central density begins to increase. It has a flat part and an R⁻² part. So essentially, assuming that we have a power law density profile everywhere is equivalent to just averaging out the entire density profile to a single power law. So that's a trick, but that allows us to understand how the central part evolves. And we also assume that the velocity at any point in the collapsing object is given by the gravitational velocity of, due to the mass contained up to that radius. Okay, so just gm of r over r, and that's the gravitational velocity. Just is the square root of the kinetic energy of the gravitational energy up to that radius. So introducing the power law density profile into the continuity equation of fluid dynamics and also the gravitational velocity, we were able to derive an equation for the evolution of the slope of the density profile. So essentially, we were able to look at the time derivative or the evolution of this inclination of the mean density profile. And, you know, it's a sort of complicated equation, but this is only a number. This is just radial dependence, which tells us that, yeah, our assumption of a uniform, of a same slope is not correct, because actually the growth rate of the inclination depends on the radius. But let's forget about this for a second and just look at the coefficient here. This coefficient, you can see that it becomes, that it is positive if p is less than 2. So if p is less than 2, then this coefficient is positive, meaning that the derivative is positive, and so the slope increases, the steepness of the slope. On the other hand, if p is larger than 2, then this is negative, and then the slope decreases. So that means that p equals 2 is an attractor. The slope wants to go to a value of -2. And that is very interesting, because, for example, in the same paper, Frank Xu went to great lengths to try to understand why in the world do we have an R⁻² density profile in the collapsing stage. And he basically argued that we needed to keep a subsonic regime so that you could have pressure waves traveling through the medium and establishing pressure balance everywhere. And so thinking in terms of a Bonner-Herbert sphere, right? And so in a Bonner-Herbert sphere, you have this profile because you have detailed pressure balance, pressure-gravity balance. And that's what gives you the R⁻² slope. Very interestingly, this slope of -2 can come out just from the prescription that the velocity is the gravitational velocity, and that the infall speed, it just comes from the fact that you see that p equals 2 is an attractor. So the slope wants to settle into the slope of into a value of -2. So you don't need any argument of pressure balance. All you need is to say, okay, I have self-gravity and I have an increasing density. And then what is, I'll get back to why this happens. Now, a note, however, is that real cores seem to saturate at slopes. Here, mu is p. Sorry for the different notation. But in that same paper, we collected a number of various reported values of the slope of the cores, and we found that, interestingly, the slopes, the most likely slope, the mean of the values of the slopes, is typically less than 2. So somehow something keeps the profiles from actually reaching that limit where they are wanting to go. And in some other paper, we gave a few arguments as to why that can happen, but so far it's essentially speculation. But the fact is that observed cores most often do not have a slope of -2. They tend to be less than that, unless they are underestimated for some reason. And I gave this talk somewhere else, and somebody made the comment that the slopes might have been underestimated. But, at face value, the slopes tend to be lower. Another very important thing is that you can compute the accretion rate just due to the gravitational pull of the mass interior to the center. So the accretion rate is just the density times the velocity. This is the mass flux. And then times the surface area gives you the accretion rate across a surface of radius r. And again, you get a number, a coefficient, and you get a radial dependence. So you get the accretion rate depends on the radius, except when p equals 2. If p equals 2, this exponent goes to 0, and then this becomes radius independent. So the slope of -2 for this spherical core is the slope that makes the accretion rate be the same at every radius. So if the mass the core accretes from the outside is the same that the mass it transfers to the stellar content it has in the center. And but that's only for p equals 2. Now, if p is, for example, less than 2, then this thing decreases inwards. And so that means that the accretion rate slows down as you move to the center. What does that mean? It means that the gas sort of loses stamina and it gets stuck in the way and it doesn't make it all the way to the center. So the gas stagnates in the gaseous phase and sort of doesn't make it at 100% efficiency all the way to the central stars. And so we, in this paper in 2024, we call this process gravitational choking. And this is because this is a purely gravitational effect. People keep asking me, okay, but what's holding the gas? What's preventing it from continuing all the way to the center? And nothing. It's just that the mass internal to that radius cannot keep accelerating the gas at the same rate. So that's it. Gravity just cannot keep pulling the gas inwards at the same pace, and therefore the gas stagnates. And this is very interesting because then the whole system increases its gaseous mass. And this explains our observation from numerical simulations that the clouds grow. The clouds grow over time. So, for example, in this paper by Vianney Camacho in 2020, we looked at a cloud defined by density thresholds. So, for example, I'm afraid you cannot see them, but this is the blue dots correspond to gas that is above 1,000 particles per cubic centimeter. And the other thresholds are the cyan points are above 3,000 particles and the orange points are above 5,000 particles. And this is at some time during the simulation in which we said that this cloud, which is a few parsecs across, is like a low mass, almost quiescent molecular cloud that is barely forming stars. A couple of mega years later, the cloud for the same lower threshold of 1,000 particles per cubic centimeter has grown significantly. It has become filamentary, but now the density contrast is much larger. Now the next contours are at 10 to the 4 and 10 to the 5. So while here the density contrast was just a factor of 5, here it is 2 orders of magnitude. Besides that, the cloud has grown in size and its mass has grown. So these are curves of the growth of the mass of the cloud's mass over time for each threshold here. So for example, this is the mass of the cloud at the first threshold of 1,000 particles per cubic centimeter. And you see that in a couple of million years, it basically doubles its mass. The density contrast, like I mentioned, grows. And this is consistent with the fact that the density profile is steepening. So the clouds grow and that they increase their dense mass fraction. And even more surprisingly, when I think I've mentioned this in some previous talk here before, but this is a result that actually, well, the first time I saw it, I thought it was a numerical error. Because even in simulations that are forming stars, and with feedback. So this comes from another paper with Alejandro Gonzalez, where we have simulations with feedback and without feedback. And the solid lines are simulations with feedback, and the dotted lines are without. And what this is showing is the evolution of the dense gas mass within spheres of the indicated radii here. So the magenta line is the radius, is the material, the mass, the dense gas mass is inside a 1 parsec sphere. The blue line is the mass inside 2 parsecs, and so on and so forth. And you see that the mass just keeps growing. Interestingly, the zero time in this in these plots corresponds to the onset of star formation. It corresponds to the moment when the zinc particle first formed in the simulation. So this other plot shows the stellar mass contained within the same spherical regions. And it shows that it's increasing. It increases a bit faster for the simulation without feedback, but it's increasing nevertheless. But what happens is that the gas mass keeps increasing even though it's forming stars. And this is what I say when I said, oh man, this must be wrong. How can it be transferring mass to the stars and yet the cloud can continue to grow? Well, now we think it's because of this gravitational choking mechanism. And this has another very important implication. The star formation, because the cloud mass grows in time, even after it's begun to form stars, that means that the measured star formation efficiency, which is normally defined as the stellar mass divided by the total mass, so gas mass plus stellar mass, this is typically interpreted as the fraction of the gas mass that goes into stars. But if the cloud is accreting, then you can keep increasing the gaseous mass, and then this thing never grows. So as long as the cloud keeps accreting, you can keep a low apparent star formation efficiency just because the cloud is accreting, not because something is preventing the gas from going into stars. It's just, and so the star formation efficiency basically becomes a measure of what fraction of the cloud's mass goes to stars to a measure of how fast the cloud is accreting versus how fast it is passing its mass to the stars. So in summary, the density profile approaches an r to the -2, but may not reach it for reasons that we can speculate about, but we are not completely sure. But this r to the -2 is an attractor. During the evolution, the mass and density contrast of the clouds increase over time, and this can be a consequence of this gravitational choking mechanism. And it means that the accretion rate, the gravitationally driven accretion rate, decreases inwards for slopes less than -2, which is exactly what we see happening. We see that the slopes in our clouds are slightly less than 2, and that explains why their masses are increasing. And then here, what I just said, that accretion completely changes the meaning of star formation efficiency. It should not be thought of anymore as the fraction of gas that goes into stars. It should be thought of as the competition between the accretion rate onto the clump versus the accretion rate into the stars. And we have discussed that in a paper with Javier in the last year. And I think I'm done. Like I said, I still have like a full extra talk here, but I can just go to my conclusions, and I would like to go over the conclusions and then I can take questions, because this is essentially the new material anyway. So first, sometimes I get the question, but why are you looking at spherical collapse, solutions that were done in the 60s and the 70s? But sometimes abstraction is crucial to really understand the basic physical processes. And I think here, for example, we would have not understood this gravitational choking mechanism if we hadn't done this. And that probably translates into something that is really happening in the simulations. The gravitational collapse is a flow. So it's setting up a flow all the way from the low density to the high densities. And it's just not just a single event. It's just a flow that is feeding material to denser and denser regions until you reach the stars. When you consider realistic collapse, it should be dynamic already during the prestellar stage, contrary to the standard, the classical inside-out collapse from Xu, which he did for very valid reasons. I mean, basically, it was the only way of analytically solving the problem. But the problem is that the initial condition was probably not very realistic. And when you consider realistic conditions, then you see that the outer speed is not zero. The prestellar stage occurs from the outside in rather than from the inside out within the scale of an initial Jeans length. One thing I didn't mention is that this boundary that marks the transition between the inner and the outer part does propagate outwards during the protostellar stage. So that can be considered like an inside-out part of the collapse. So my picture is that you have outside in, inside the initial Jeans length, and inside out, outside the initial Jeans length. But that's something that we need to test. The initial, already I didn't have time to mention this. But here the non-self-similar evolution, the density profile steepens and approaches an r to the -2 profile. The radial profile of the accretion rate depends on the value of the slope. This is crucial, and this leads us to gravitational choking. And this is what might explain the growth of the clouds at the same time that they're forming stars. And then one part of the talk that I didn't have time to mention, but this leads to the notion that by the time you form massive stars, your core must be massive already. And so this would go in the direction of explaining the observation that the most massive star in a cluster tends to be more massive the more massive the cluster is. So the most massive star is more massive when the cluster itself is more massive, signifying that the growth of the masses inside the cores that form them and the growth of the cores go hand in hand. And I would leave it there. Thank you very much.
Okay, so naive question. I didn't hear any mention of radiative cooling and magnetic fields. Are they at all important in determining the gravity?
Yeah, definitely. Well, radiative cooling is sort of built into these studies when you consider isothermal. No? Because in order to keep a fluid isothermal, you need to cool it somehow. So, but molecular clouds are close to being isothermal. The cooling processes going on in molecular clouds keep them more or less at the same temperature until stars begin to feed back. But yeah, so cooling is important, but it's essentially built into the assumption of isothermality. And magnetic fields, yes, Ruben, my grad student, is doing a study of the delay in the collapse introduced by the presence of a magnetically supercritical field, meaning the field is not strong enough to prevent the collapse, but it is capable of slowing down the collapse to some extent.
It has pressure, so
exactly. So basically, but to us, the main effect is that it slows down the process a little bit. But as far as the growth of the clouds and the sequential timing of the collapses and all that, probably it just makes it all happen a little bit more slowly.
Roberto? Yeah, so regarding the last point of the star formation efficiencies and the force growing constantly in time, so I do think it applies to some of the massive things that we see. The paper of Thomas where the protostellar cores are more massive on average than the prestellar ones. But if you apply that,
the protostellar are more.
Yeah, so the CMF of the protostellar cores is flatter than of the prestellar, and therefore they also the average mass of the protostellar cores is higher than the prestellar.
So you think she applies?
So the interpretation that we gave is very similar to this.
Okay.
I think I don't know which paper appeared first, but regardless of that, that's for the more massive things that we see. But if you think it applies to every single cloud and inside clouds to every single core across the galaxy, wouldn't this imply like the original problem from the 70s that the global star formation rate of the galaxy is too large, or that the mass reservoir is too large?
I didn't touch on that, but
galaxies have a duty cycle, gas. So wouldn't this imply that you have like a Star Wars everywhere and infinite molecular gas?
Thank you for the question. I didn't pay him to ask that question. No, of course, that's another part of our model. Precisely because the gas does not reach the center all at the same time. So that allows you to form massive stars. That's also built into the 2024 paper here that I showed. You can track the moment at which a sufficiently massive star with a sufficiently powerful radial flux appears to truncate your accretion.
So you turn on feedback and then that...
We turn on the feedback and then cuts the process. That interrupts the process. But what's very interesting is that in the 2024 model, it's all self-consistent because the growth rate of the gas tells you what is the growth rate in the mass of the massive stars, and that tells you what is the growth rate of the most massive star that you can find inside, and that tells you what is the growth rate of the available feedback power to interrupt. So it's all interconnected. And so we're thinking of trying to apply these models to a suite of, to a survey that has been performed. So to check whether the timescales that we obtain with the model are checked with the timescales that are inferred from the observations.
Muy bien, Enrique.
The native English speaker speaks this.
So I know you said you were not going to talk about anisotropic collapse, but I'm wondering if the attractor you find with P = 2, how that depends on the geometry. You get the spherical symmetry. If you were to use cylindrical symmetry, would it still be P = 2?
I think it is not, right? Yeah. The value of the exponent changes given the geometry. Although the other part of the equation here is that what we have realized is that the gravitational potential, for example, is obtained by integrating the density twice, no? Because we have the Poisson's equation that says Laplacian phi equals 4 pi g rho. That means that essentially the gravitational potential is a sort of low pass filtered image of the density. So one thing we want to investigate now is to what extent that really makes the gas not care too much about the detailed shape of the density structures that it has inside. As long as you average it spherically, is the result essentially the same? One very peculiar observation is that the mass size relationship that you obtain for a linear filament, uniform density filament, is just mass goes linearly, increases linearly with radius. That's exactly the same rate, mass size relation that you get from a R2 to -2 density, spherical density profile. I don't know if it has any meaning or it's just a coincidence or it has a deeper meaning, a geometrical meaning.
One other comment, you talked about the kinematic signature of infall in the line profile. And said that you thought it might be modified. But I'm not sure it would make a lot of difference because, as far as I understand it, it's the sign of the velocity that's most important in determining that you get the blue shifted higher. The fact that you've got a different velocity law would make a difference to the details, but I'm thinking would actually change.
In fact, we have a paper that has been, like I said, dormant for several years. But I think the main consequence of that is that the speeds that you infer are going to be an underestimate of the actual infall speed. That would be, and that the actual parts of the profile come from different parts of the core than were depicted in that picture. So is like the tomography of the core is different. But the most relevant part is that I'm pretty sure, and our preliminary results support the idea that the main effect is that now you have the larger velocities further out where the density is lower, and therefore you may be your peaks in the profile perhaps will be sampling not the largest velocity impulse speed, but some intermediate. So I'm thinking that it might be an underestimation, perhaps by a factor of 2, but that's enough to make a subsonic, an apparently subsonic profile supersonic.
Won't it depend on the choice of that? Because
That's
different molecules come from different radial zones. So a given molecule would be selecting out. So maybe
definitely, yeah. So that's still pending, but so that's why I just posed it as a question.
Emilio?
Yes, probably it's related with Will's question about geometry and dimensions. But I was thinking that inside-out process is easier to conceive, no? Because it's something that is propagating from a specific place. Instead, this outside-in process, which is very appealing, but when you think about the boundary conditions, as you said, it's like if all the universe were going through to that same place. But you explained how you can go around that, but in any case, it's like difficult to imagine why different parts of a sphere will start going towards a single direction.
Well, the way I imagine it is, it all goes to the initial condition, basically. And the way I imagine it is, if you start from a finite density medium, you do have one Jeans length associated with that medium. No? So there's one value of the Jeans length for that. Well, the smallest thing that can begin to collapse is of the size of the Jeans length. So you cannot think that nothing was collapsing here. Your collapse occurs on the scale of the Jeans length and inwards. And that's why I'm saying it's outside in from the background Jeans length inwards. And it's probably inside out from that scale outwards. That is something, the second part is something that we still need to test numerically. But that way, it's not a problem. It all comes back to the fact that Xu chose the singular isothermal sphere as the initial condition. So he sort of bypassed the problem of how do I get to a singularity? Oh, let's just put it there. No? But if you want to see how you get there, you need to consider collapse from larger scales.
Thank you.
More questions? Do you have questions on that?
No, unfortunately.
Okay. So let's thank Enrique again.
Thank you.